So today we have two concepts to discuss. Number one is density, and number two is pressure in liquid, and they're related because this is an introduction to the fluid chapter. So we have a list of density here. Let's get familiarized with the density. This is actually ordered in increasing amount of density in kilograms per cubic meter. As we see, gases have very low density in the singles or even a fraction of one. And then we have some styrofoams, corks, and wood that is lower than about 1,000. Cooking oil is close to 1,000 with ice, and fresh water is 1,000 kilograms per cubic meter. This is a nice point of reference. The water's density, because we can tell that denser than water and less dense than water will be sink or float. And salt water is slightly denser. Plastic usually denser, but could also be less dense. Certain plastics, and concrete is denser. And starting aluminum, this is now we have metal, and most metal are denser than aluminum. We can see there's titanium, there's also iron and brass. Brass and nickel are very close, and also close to copper. And then we have lead, pretty dense, and used to be common metal. And also mercury is dense in the liquid in liquid form. And then we have tungsten, gold, and platinum. And if we keep going down, there's actually even denser materials such as white dwarf stars and neutron stars with densities just unimaginable. There's a huge gap in between what we can see on Earth and what's out there, rest of the universe. So let's review density. Density is rho, and is defined as mass m over volume v, and this gives us the unit of kilogram per cubic meters, and 1,000 kilogram per cubic meters is actually equal to 1 gram per cubic centimeters, and that's the same as 1 gram per milliliter. Okay, so if you see some numbers that are only in the singles, for example, if aluminum was quoted as 2.7, that is in grams per cubic centimeter instead of in kilograms per cubic meter. All right, and to find mass, we can use the same formula, and mass is density times volume. And we can also find mass if we have an area density of sigma, and we know the area, then we can find the density of a planar piece of material. This is a volume. And then if we have a rod or maybe a wire or anything that is very elongated, we can use a linear density L times the length of that material to find the total mass. We usually purchase things per quantity of mass, such as say if you purchase some electrical wire, you can go to a hardware store, just cut a certain length, and they charge you per the length because the density is a constant, so the mass is scaling with length. And other places, say you buy some sheet metal or maybe some wooden boards, and they'll be selling you more or less proportional to the area. And then yet other places, if you buy things per bulk volume, and you'll be charged per volume, and that's proportional to mass. So now that we know the relationship between density and mass, let's move on to the right side. We'll discuss pressure in liquid. So this is an empty beaker. Let's fill it with some water. So give it a blue surface. This is the top is air and the bottom is water. All right, so our goal here with this diagram is to figure out the pressure inside of a liquid. Actually, we can also figure out pressure inside of air, but since water right here, water is 1,000 times as dense as air, we're ignoring the fact that air also has density and also there's pressure. So let's imagine this is a small volume inside of water. This is actually enclosing water, just water inside of water. So the edges I was drawing were imaginary. Just imagine here's a volume of water, and the top and bottom surfaces have area A. So we'll put A here, and the top surface gets pushed down with a force F top. At the same time, the bottom surface gets supported upward with an F bottom, and this whole volume also gets weighed down, pulled down by gravity Fg. And this volume it stays static because the three forces balance each other and one another. So let's find out these forces and how they're related to each other. We'll start by finding the mass that we just enclosed using the density formula. Is density times volume, and that will be density times surface area times height. So this is height h. Alright, we have height h. So that's our mass. And then according to Newton's second law, with static equilibrium, upward forces and downward forces are balancing each other. So we have upward force Fb minus downward force Ft minus downward force F gravity equals 0. And the force on the top over the area will be pressure, right? We understand that already. So pressure is force over area. So pressure on the top and pressure on the bottom, they basically have the same area. The forces are different, so the pressures are different at the top and the bottom of this imaginary volume of water. So this force on the top should be equal to pressure at the top times area. Force at the bottom, bottom and then top is pressure at the top times area. So we replace these forces and those with what we just got. So bottom pressure times volume area minus top pressure times area minus mass gravity equals 0. And we can replace mass with this expression so that we have pressure bottom area minus pressure top area minus rho g h also times area equals 0. So since area is a common factor, we can divide it out. So pressure at the bottom is equal to pressure at the top of that imaginary surface plus rho g h. So this gives you a relationship between the pressure at a certain depth and the pressure at another depth. So to make this a bit more easy to use, let's set up a coordinate system that starts from the air and water interface and points down. So the coordinate increases as you increase depth. This is a pretty typical way to describe depth increasing, right? So here we have a y-axis. Y is 0 at the interface, and at the bottom, so let's call it y2. At the top, let's call it y1. So we have pressure at 2 equals pressure at 1 plus rho g. The h is the difference between the 2 and the 1, so y2 minus y1. All right. We can also describe this as so p y2, right, equals p y1 plus rho g y2 minus y1. Okay, so let's assume there's this pressure here. We'll have it on the left side. The pressure 0, this is the pressure at y0, or pressure at y equal to 0. So that's pressure right here at the air and water interface. So the pressure of the atmosphere. Normally, I say normally. Well, normally pressure at this is just the pressure at the atmosphere, which is 1 atm. So let's say approximately equal. It depends on where you live and also depends on the weather. So this 1 atm is exactly defined as 101,325 pascals. Alright, so this is a well-defined value right here, but the pressure is not necessarily a 1 atm. So unless it's given otherwise, we can assume it is 1 atm near Earth's surface. So if we use this P0 as our P1 here, then we can do this change. So this P2 or P at a y will be equal to P1 is our P0 plus rho g, and now y2 minus y0, which is a 0, so this is a y, or sometimes we just say an h. This h is a depth. H is depth from air-water interface, or the water surface. Alright, so now that we know pressure, how pressure can vary with depth, pressure is proportional. Well, the change of pressure is proportional to depth, or pressure is linear with depth. So let's have an example. We'll calculate pressure. Let's not use that at 10 meters below water surface. Okay, so we have rho, which is equal to 1,000 kilograms per cubic meter for water, and this P0 will take at 101,325 comma Pascal, and then we'll use H equals 10 meters, and also with G, so we can calculate pressure at 10 meters equals pressure 0, which is 101,325 plus density of water 1,000 times gravity 9.8 times depth 10 meters. So we have 101,325 plus 98,000. So you add them together, this is approximately 2 atm. So if you're diving 10 meters below water surface, then you're going to have this pressure that's equal to 2 atm. We call this absolute pressure. Absolute pressure. And there's also this pressure. We'll put a G here for gauge pressure, that is defined as absolute pressure minus the pressure at 0. So this gauge pressure at 10 meter deep is just the 2 atm minus the 2 atm minus the 1 atm at the surface. So this is 1 atm. So what is a gauge pressure? Gauge pressure is measured by a gauge. So assume that the gauge is constructed this way so that it will show 0 at atmospheric pressure, which is what most old gauges are doing. And then you take the gauge into water, and it starts to measure how much higher the pressure is compared to when it was in the atmosphere. So it will show that it's 1 atm higher than atmospheric pressure. This is a concept that's typically used in say pressurizing your car's tires or balls, any ball gains pressure, and they're all using gauge pressure.